Thanks. Sorry, the speaker is Prasanta Kumar Guha. Yeah, and then that's fine. So I would like to acknowledge Sayan, Sumita, and Professor Sumit Ray. Okay, and I would like to talk about temperature tunability of our device for detecting couple of VOCs. Okay? So this is the content of my talk. I'll give a general introduction on air quality monitoring. I'll talk about different sources. Particularly, we are targeting 3 VOCs: formaldehyde, toluene, and 2-propanol. So I'll talk about their sources and their effects. Talk about our material synthesis, general characterization, and our simple device. Show you some results. And propose a mechanism which explains, try to explain the reason for this selectivity, and at the end I will conclude my lecture. So we all know that both indoor and outdoor air quality is very important. Particularly indoor air quality is important because we spend most of our time indoor. There are different reasons for this quality degradation of air, which hampers human health. For example, fuel adulteration, particularly in India, vehicle emission from vehicle and factories, rapid constructions, etc. And in indoor, the factors are fuel wood, biomass burning, paints, furniture, etc. and etc. So air pollutants, these are different air pollutants. For example, there are different VOCs, there are some inorganic gases, particulate matters, and the situation is not very good because there is lack of awareness and understanding among common mass of this long-term acute effect of air pollutants, and also a lack of implementation of tougher regulations. This is particularly valid in case of India. Now, as I said, that we are targeting 3 VOCs: formaldehyde, toluene, and propanol. Formaldehyde is one of the main VOC for indoor pollutant, and this is present because of the resin and adhesive and varnishes in furnitures. Okay. In case of toluene is basically methyl benzene. We use toluene quite a lot for benzene production, and we use toluene as a paint thinner. Okay. As far as the propanol is concerned, nowadays propanol is a very lucrative preservative for biological specimen in place of formalin. So these are typical VOCs we often use, and these have similar kinds of effects on human health. For example, depending on how long we are exposed to these VOCs, for example, tiredness, confusion, breathing problem. Particularly formaldehyde is carcinogenic in nature. So these are different effects on human body for these VOCs. Now, there are many different air quality monitoring unit out there commercially available. Most of them uses electrochemical type gas sensors. They are very expensive, and almost all of them uses total VOC rather than individual VOC. So if you buy a air quality monitoring system, it often tell you total VOC, not the individual VOC if you want to look. So that's one of the motivation we target to develop a sensor which will selective to couple of VOCs. So we use 2 material. One is nickel oxide and one is iron doped nickel oxide. These are p-type material. One reason for p-type material, using p-type material, although I don't have results to show that, but we have loads of results in the lab showing that p-type material is water resistant, or is not very sensitive to water or humidity. So we use p-type material, for example, NiO. So how you make NiO? We start with NiNO3 whole twice. We dissolve it in DI water, and we add dropwise NaOH 0.1 molar solution, and it gives us a green precipitate of NiOH whole twice. We then disperse it in DMF solution and sonicate it for 8 hours to get a exfoliated NiOH whole twice. Okay, so this is a green color solution. Now the other material we use is FeNiO. For that similar approach we adopt, but we use urea and iron sulfate. and we use a surfactant PEG, which ultimately gives upon steering, which gives a yellowish green solution, and we put it in autoclave for around 3.5 hours at 100 degrees centigrade, and we end up with FeNi OH whole twice. Then we calcined around 450 degrees centigrade, wash it in dry water, and so on and so forth. We get a dry powder of FeNiO. So these are the two materials we have used for our device fabrication. This is the general material characterization. We have done XRD, we have done SEM, so this is the NiO layer, and on top of that there is FeNiO layer. This is EDAX, just to see that the materials we have made is exactly that, those materials or not. So this is the simple sensor device. This is the schematic of the device. We started with a glass substrate, ITO coated glass substrate. We etch the ITO from certain portion to realize the bottom electrode. Then we deposit NiOH whole twice, nickel hydroxide nanosheets drop cast method on top of this bottom electrode. And then we basically grow FeNiOH whole twice hydrothermally directly on top of this. So this is we put in the hydrothermal chamber, and then we calcined it, so that makes that gives us FeNiO and NiO. Okay, and ultimately we take top contact as an AU electrode by thermal evaporation. So this is our sensor device. I'd like to show you some gas sensing results. We found that there are optimum temperature for these three VOCs at 200 degrees centigrade and 250 degrees centigrade and 300 degrees centigrade. We have done the gas sensing for loads of other VOCs, for example acetone, ethanol, methanol, benzene, and so on and so forth. And we have found that only these three, the sensor device is selective to only these three VOCs at these temperatures. Okay, so 2-propanol, toluene, and formaldehyde. So these are the gas sensing results. We vary the VOCs from 4 ppm to 76 ppm. So this is 2-propanol. We get response around 1.9 times. By times I mean that is R2 by R1. Okay. So this is the response of toluene, and this is the response of formaldehyde. With formaldehyde we get the highest response, around 2.1 times at 76 ppm, around 300 degrees centigrade. So its optimum response achieved 200, 250 and 300 degrees centigrade. So what we also did, we check the biasing effect of the device. So we apply forward bias. By forward bias I means the positive supply, positive supply is connected to FeNiO, and we see that the response is quite large if we apply the positive supply to FeNiO, whereas if we apply the negative supply to FeNiO or positive supply to NiO, the response is quite poor. Okay, so this blackish gray line is when positive supply is connected to NiO, whereas this red line is for when positive supply is connected to FeNiO. So this is only I am showing for only for toluene sensing. The similar thing happens for formaldehyde and 2-propanol as well. So I would like to explain the sensing mechanism behind this result. We think that when we are increasing the temperature, we get more and more minority carriers. Those minority carriers here basically electrons, because this is both FeNiO and NiO is a p-type material. So electrons will be near the surface, and they will help in forming oxygen as adsorbers. So the more the number of electrons near the surface, the more will be the oxygen adsorbers, and so the probability of getting more response will be the probability of getting response will be more when the number of electrons near the surface is more. So this is the order of oxygen adsorbers needed for three different VOCs. For example, for formaldehyde, the oxygen adsorbers requirements is the most compared to that of 2-propanol. Okay, what about so that is why we need higher temperature in case of formaldehyde than in case of 2-propanol. Now what about the biasing of the device? When we apply positive bias, the current is basically flowing, whole current is basically flowing from FeNiO to NiO, but as we are applying positive voltage, the electrons are near the surface of the device, and then those electrons get chance to trap, I mean those electrons will be trapped by oxygen adsorbents. Okay, whereas when we reverse the bias, the electrons will be pushed at the junction, near the junction of the device, so less number of electrons are present. So I have a schematic to show that. So this is the supply is connected here, and the more number of electron is near the surface, top surface, and they get chance to be trapped by these oxygen adsorbents, and so chances of sensing will be more. Whereas when you have the opposite situation, the electrons will be pushed to the junction, so less number of electrons are present, so the sensing response will be much less. So this is what we have seen when we bias the circuit, bias the device differently. So in this work we show that we can change the selectivity or improve the sensitivity not only by temperature but also by proper biasing. Okay, so this is as a conclusion, I would like to say that we have developed FeNiO based sensor device, and the sensor device was developed on ITO coated glass. Okay, through this sensor device we can get selective response from the VOCs. We have targeted 3 VOC, 2-propanol, toluene and formaldehyde. With the help of biasing we can also improve the response, and such sensors show good potential to detect different VOCs selectively. Okay, so thank you for your attention.